All right, so we're looking here at 11.1 part 3. So all of the material covered in your textbook section 11.1, there's a lot there. We have a total of 5 lessons in this little unit, and 3 of them are just that one section. So what we're going to be looking at today are continuing to practice with permutations. We're going to be looking at something called pathways problems, but most importantly, we're looking at repetitions. And I'll explain to you what that means in a second. And if you understand how to deal with repetitions, you will be able to work with pathways and solve pathways problems. So what we are interested in today is finding the number of arrangements of items if items are repeated. And by repeated, I mean they are identical. Okay? You cannot distinguish between them. And we're going to apply that to pathways and continue to solve permutations problems. So as an introduction to where we're going with this is not in your notes, but let's imagine that I have 3 Snickerdoodles cookies. And these cookies happen to be, if you look at them carefully, they happen to be identical. But of course, I know when I make Snickerdoodles, they're not all exactly the same. But they are all Snickerdoodles. Okay, so in terms of the taste sensation, it doesn't matter which one of these I eat. It's eating a Snickerdoodle. These are all the same in terms of my mind. And I also have 2, I guess I can call these M&M cookies. And then I think I'm going to have 4 chocolate chip cookies. So the question is, how many different ways could I eat all of these cookies in terms of order? I could be a very organized person and eat Snickerdoodle, 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 M&M, M&M, chocolate chip, chocolate chip, chocolate chip, chocolate chip. And then I would sit there in my shame and go, well, that's one way I could eat 9 cookies all in one sitting. But how do we approach this problem mathematically? Well, we have to assign labels to these things. And the question then becomes, how many different ways can I arrange those 9 letters? If I had 9 Scrabble tiles, I might need multiple Scrabble tile sets. I don't know. I don't think you have 4 C's in a, maybe you do. Doesn't matter. If you had 4 Scrabble tiles that had C's on them and 2 that had M's and 3 that had S's, the question is how many different ways could you arrange those tiles in a row? Because each arrangement, for example, this arrangement is a particular, it represents a particular order. This is a very organized way of doing things. I want variety, so I eat a chocolate chip, a Snickerdoodle, and M&M, a chocolate chip, a Snickerdoodle, and M&M. I'm out of M&M's, so I go chocolate chip, Snickerdoodle, whatever. That is a particular order. And if I were to switch the order of these first 2 cookies, so if I had a time machine and I could go back and I say, you know, let's eat a Snickerdoodle first and then a chocolate chip, and then I'll keep the rest of the order the same, I get a different arrangement, don't I? Now at this point in time, if you look at the letters, there are 9 letters. Can you figure out for me what 9 factorial is? I have no idea. I'll recognize the number probably, but other than that, I would never know. 362,880. 362,880. 362,800. But the thing you need to understand is that is not how many ways to arrange these letters. Because if I decide to look at another arrangement of these letters by taking my Scrabble tiles that are already arranged as SCM, CSM, CCS, and I do this, I change those 2 to get one of those 362,800 arrangements, I get the same arrangement. So if you list all of those 362,800, many of them are already going to be taken. They're already accounted for. So it's fewer arrangements because we have identical items. This kind of question can manifest itself in dozens of ways. I could say that you have these vehicles in a car lot. We are all aware that the blue vehicles are different. They have different vehicle identification numbers stamped somewhere on the vehicle engine and elsewhere on the body. You know, the interiors might be slightly different, but for all intents and purposes, those 4 blue vehicles are the same in the same way that those 4 chocolate chip cookies are the same. When you look at the situation, you see the cars, they're blue. So the question would be, how many ways can you park those in a line? And it can get more complicated than this, and we'll encounter situations. But we translate that to how many ways can you arrange these letters? B, 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 R, 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 M, M, M. M is magenta. Okay. I once bought a truck in 1998 that had magenta pinstripes, and I didn't know what color that was. And I had a very bright, pinky, pinstriped vehicle. Okay, so let's now get back to the lesson here, or get the lesson started. If I asked you how many unique, which means different arrangements of the 4 letters of the word past are there, that's really a trivial question to answer, isn't it? 4 factorial. Which I'm guessing that everybody knows is 24. And I decided to list them all. You don't have them listed in your handout, but if you look up here, there they are. I got a lot of time on my hands, apparently. So those are all of the arrangements. Past, pats, sat, sta, tas. You can't pronounce them, but they're arrangements. They're not words. They're arrangements. And spat, tas, taps, they're all there. Trust me on that. The question is now, how many unique arrangements are there of all of the letters of the word pass? And I want you to notice that when you compare the word pass to past, what's happened is in past, where there's 4 different letters, that T at the end is now going to become an S. And we're going to have 2 S's that are identical. But what that means is that in this list for past, if I change this T at the top of the screen to an S, every single T in this list becomes an S. And if you keep your eyes on the screen carefully, you can see that that's all that I've done. I've gone through and I've edited that page. I've cloned the page and edited it, and every single T has turned into an S. So when you look at these 2 words, arrangements, they happen to be words, but that's not important. When you look at these 2 arrangements, they are different when we look at the letters of the word past. But if this T in the first arrangement and this T in the second arrangement are both going to become S's, then they become the same thing. I got to try to get rid of that yellow thing. It's driving me nuts. And you're going to discover that if you go through that list here, and you do that, you change all of the T's to all of the S's, you're going to find pairs of 4-letter arrangements that become the same. So, for example, I have this one where the S and the T are in the middle, but the S is first and then the T. So someplace there's the same thing right here, where the 2 letters, S and T, are in the middle, but they're in a different order, so they count for twice as many arrangements of the letters of the word past. But what's going to happen with these 2, keep your eyes on these 2, is they're going to become the same. And the result is that we're going to have half as many. And you can go through and you can identify all of the ones and cross off the doubles if you want, if you had this written out. I feel as though I don't need to do that. Like just in the first row, I had 6 different arrangements, but I happen to, and it won't work out the same for every row, I happen to have 3 pairs that are identical now. So we get half as many, and that's why the answer is 12. You with me? So now, what about all of the letters of the word SAS? So let me bring back now the letter arrangements of the word pass. And we're going to change pass to SAS. By the way, I've got 24 listed here, but we know there's only 12, right? Because some of these are repeats. They're identical. So I'm going to change this P to an S to make, I go from past to pass to SAS. And what that means is just going on, well, lots of these, every place there's a P, the P is going to become an S. And the result is you really don't have very many arrangements. You have SAS. You have SAS. But instead of having those 6 that I've marked with the pen, those 6 that were different, well, these, we already marked off that one, right? But those other ones end up being the same as the word SAS. So you only have 4 unique arrangements. You have SAS, you have AS, you have SA, and you have SAS. I don't know how you'd pronounce all that stuff, but you get my drift, right? All of a sudden, we've gone from 24 to 12, and now what we have are only 4. So what do we learn from this? We learn that if there are 4 unique items, there are 24 ways to arrange them. If there are 4 items but 2 are identical, this would be like a peppermint chip cookie, an all-in cookie, and 2 snickerdoodles. An all-in cookie is what I make when I just don't know what to make, so whatever I have goes all in. I just open the cupboard and I just fill it with whatever. There are only 12. When I go to 4 items where 3 are identical, it all of a sudden drops to 4. The question is, what's going on here? Well, to go from 24 to 12, you divide by 2. And to go from 24 to 4, you divide by 6. But where is the 2 coming from? And where's the 6 coming from? Well, and you can reason this out with a little bit of logic, but the 2 is actually 2 factorial. And the 6 is actually 3 factorial. There are 2 items that are identical in the word pass, and that's why you take the normal number of arrangements, 4 factorial, and you divide by 2 factorial. But it turns out if you have 3 identical letters, then you take the normal number of arrangements, you go 4 factorial or 4p4, and you divide by 3 factorial. And that's the new thing today. That's what we've learned today. Now we just have to put it into practice with a few examples. In general, when arranging n items where one of these n items is repeated multiple times, and another is repeated multiple times, and another is repeated, then you find the number of arrangements as if everything is different, and then you divide by all of the factorials of anything that are repeated. Now, in my example here, it's just one thing that's repeated, the letter S, in both pass and SAS. But if I go back to this, if I say how many different ways can I arrange those 9 letters, which means how many different ways can I eat those cookies, and I can't eat part of a cookie and then another part of a cookie. I have to eat whole cookie, whole cookie, whole cookie. The answer is going to be 9 factorial because there's 9 of them, but then I have to divide by that. I have to take whatever 9 factorial is and divide by 4 factorial because there are 4 chocolate chip cookies, divide by 2 factorial because there are 2 M&Ms, and also divide by 3 factorial for the 3 snickerdoodles. So let's talk about your calculator briefly here. This is something I feel I shouldn't have to explain, but you never know, and we're not in any real rush today. This is going to give you the wrong answer. Because what this is, there's a multiplication sign in between the 4 factorial and the 2 factorial and the 3 factorial. Whether you put it or not, your calculator will multiply. So this will be 9 factorial over 4 factorial, and then it's going to multiply by 3 factorial, 2 factorial, right? You don't want to enter it that way. You either want to put those 3 factorials, the 4 factorial, 2 factorial, and 3 factorial, all together in brackets, or how I would enter it is I would have just put divided by divided by. That's just the way I used the calculator when I was in school. Anyway, there are 1,260 ways to eat those cookies. All right, let's take a look at some here. I'm not going to work it out. It would be 11 factorial because I think there are 11 vehicles in total, and we would divide by 4 factorial because the 4 identical blue cars, 4 factorial because of the reds, and 3 factorial because of the magentas. Okay, let's get to work on the examples here. Example number 1, how many arrangements of the letters of the word calculus are possible? Well, this is like the cookies and the cars. There are a bunch of items we're going to arrange. I count 1, 2, 3, 4, 5, 6, 7, 8 letters in total. So it's 8 factorial. Now, you would be surprised how easy it is to lose track of letters in a group. It really is. So when I get to this point and I want to go divided by, I start on the left-hand side and I cross off the C and I keep going and I go, okay, there's 2 C's. And now those C's are crossed off of my list. And I do recommend rewriting the word somewhere. So that means I divide by a 2 factorial. And then I go to the A and I cross off the A, but there's no more A's, so I don't have to worry about repetitions there. I go to the L and I see that there are 2 L's. Then I go to the U, I see there are 2 U's. And then there's 1 S, so I don't have to worry about that. So this is the answer to the question. And I'm going to write down what you would probably see in a multiple choice or a numerical response. But the answer to this question is 7 factorial. And what's going to happen is you'll say, as some of you are probably saying now, how on earth is the answer 7 factorial when there aren't even 7 items? And the answer is 7 factorial because that's just what it happens to be. On the bottom, 2 factorial is 2. 2 times 2 times 2 is 8. So you have 8 factorial divided by 8, which leaves you with the 7 factorial. Which, is that 5040? 5040. So if you want an actual numerical answer, it's 5040. But it could just be written as 7 factorial because that happens to be what it is. It isn't that it's 7 factorial because of a connection of the number 7 to the question. Oh, here's a cookie question. 2 M&M, 3 Snickerdoodle. Well, wasn't this the one we just did? The exact numbers? Okay. So let's just write it out. It was 9 factorial over 4 factorial, 3 factorial, 2 factorial. You understand the order of the repetitions in the bottom don't matter? Okay, so this could be a numerical response question where it says, could be that. And the answer could be 9, 4, 3, 2, 9, 4, 2, 3. There would be a lot of acceptable answers. How many permutations, that just means arrangements, are there of the letters of the word monotonous under each condition? So no restrictions. Well, it's the cookie question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factorial. We need to divide by, I know I said you should rewrite this, but I also know that some of you have very tiny writing. It's meticulous and it's perfect and it's tiny because apparently you have really good eyes. Okay? Just make sure that you're looking at a word that you're not squinting at. Because if you start squinting and crossing, you're going to mix yourself up. So there's 1 M, that's no problem. O's, well, I've got 1, 2, 3, 4, so I need to divide by 4 factorial. N's, I have 1, 2 N's, I need to divide by 2 factorial. T's, I only have 1. And I'm going left to right, so I don't have to keep going back to the beginning and reading the same thing again. 1 U, 1 S. So that's it. This is the answer to the question. I'm going to actually work out what this is. Scientific calculators as opposed to graphing calculators always have a factorial key right there, which is really nice. They also have a NPR key right there. So we got to go hunting for this. I want to divide by 4 factorial and I want to divide by 2 factorial. I just know 4 factorial is 24. 2 factorial is 2. So the answer to this question is 75,600. Each arrangement begins with a T. Well, the first thing we need to be aware of is the fact that there's only one T. So really, what we need to do is go to the fundamental counting principle. Well, we don't have to, but let me write it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this has to be a T, and this is, as I say, who cares? Right? It doesn't matter. We have no restrictions. That's all that means. So the fundamental counting principle says that since there's one T, you put the number there as being 1. There's only one option. And then rather than me saying 9 times 8 times, I really kind of just abbreviate this and say with the fundamental counting principle, I need a T and I need the arrangements of the other 9 items. You don't have to write this down. I'm just saying we don't need to write all those blanks. We can just say that the answer will be 1 times the number of ways to arrange the remaining 9 letters. And you would normally say that's 9 factorial, except that in those 9 letters you have some repetitions. We've already identified them, right? There's 4, I think it was 4 O's, and there are 2 probably N's. Okay? So we divide this by 4 factorial, 2 factorial. And what you're going to get, and I'm pretty sure my logic is sound here, is you're going to get 7560. Because the only difference is the wrong word, but the only thing that's different here compared to there is on the top I have 10 factorial, and here I have 9 factorial. So over here I have an extra factor of 10, which means you can check it out. Can you confirm that you get 7560? Okay, so that's the answer to the question, but I wouldn't have done it that way in my head. I mean, I kind of would have, but what I would have said is the following. I would have said, if you're handcuffing me and telling me that I need to start with the T, then you're taking the decision out of my hands, so I'm not even going to worry about the T. I'm just going to say, if you're telling me the T has to come first, what you're asking me is how many ways can I arrange the other letters? So I'm looking at that saying 9 factorial over 4 factorial, 2 factorial. The difference in how I think of it is subtle, but it's just the way my brain works. If there were 2 T's, it might get a little more complicated. Each arrangement begins with an O. Okay, so I would prefer to do it my way. What I would do is I would say that this O right here goes in the first blank. And that means I want to arrange the remaining 9 letters. You with me? Okay. If that's the case, then this particular O goes here. There's only one. This is my way of thinking. I'll show you an alternate way in a second. And then I have to arrange. Okay. I have to arrange the remaining 9 items. But I'm only looking at those 9 items. And now there are only 3 O's instead of 4 left. So what this is that I'm working on here is that. It doesn't include that O that I've already put in the first blank. And that means I also have, I still have 2 N's. So can you work that out for me? What if you said this? I don't like what Mr. Wei does. He's gonna tattoo a label on one of those O's and say that's the O that goes in the first blank. What if I just want to use the fundamental counting principle and say that this must be an O, and then I have 9 more decisions to make? Well, you would look up here and you would say this is 4, correct? And then you would say the remaining chunk will be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? But then you have to divide by the repetitions. And the fact of the matter is, when you think of it this way, we had 4 O's and we have 2 N's. I don't like this method. To me, this is confusing. The difference is, up here in my method, method 1, well, not my method, the one I prefer, I'm identifying a particular O as being first. And I think that simplifies the process for me. Here, in the second method, I'm just saying I'm putting an O here. I don't know which O it is. But then in the end, I have to divide by 4 factorial and 2 factorial because there's 4 O's and there's 2 N's. But this 4 on the top and this 4 factorial on the bottom cancels to a 1 on the top and a 3 factorial on the bottom. It's going to be the same number is what I'm telling you. If you take 4 multiplied by the 9 factorial over, and look where I put the over. The over is over the whole thing. 4 factorial, 2 factorial, it's going to be the same. Because this 4 factorial is 4 times 3 times 2 times 1. It cancels with a 4 on the top to give 3 times 2 times 1 on the bottom. It's going to be the same number. I don't know. I prefer the first method. I think it's easier to wrap your head around. What about if the 4 O's must be together? Well, this is Joan and Emily, right? Do you remember when we had to arrange so Joan and Emily were together? But then we also had to multiply by the number of ways to arrange Joan and Emily? Well, we don't have to multiply by the number of ways to arrange the 4 O's. We can just take those 4 O's and put them together. We have an M, we have an N, we have a T, we have another N, we have a U, and we have an S, and we have the 4 O's. Monotonous. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what we're really arranging then is this, 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 and this. And you would normally say, and we need to arrange those items in the group. If you want to, for arranging the 4 O's, you can write times 4 factorial. And then go, oh, but 4 identical items are there, so I'm going to divide by 4 factorial. It's not going to matter. So the answer to this question will be 7 factorial divided by 2 factorial. Because of the 2 N's. And it's 7 because we have 7 left when we group 4 of them together. What's interesting, and nobody has asked me about this yet, maybe because I wasn't here when I did the lesson, what is this, 50, 40, 25, 20? 25, 20. And almost every time I teach this, somebody goes, shouldn't it be 6 factorial? Because there's 10 items, this is their reasoning, there's 10 items, and we got 4 O's that we're grouping. Well, yeah, but when you group those 4, they are an item. So you're left with not 6, you're left with 7. Okay. How many different ways can 4 yellow and 4 blue blocks be arranged if the yellow blocks cannot all be together? Well, the number of ways, we did this in the first lesson, or I did it for you. The only way to find out how many ways something cannot happen in this unit is to find out the total number of ways anything can happen and subtract how many ways that thing can happen that you don't want to happen. If I said to you, how many people in the room don't wear glasses, you could just take the number of people in the room and subtract the ones who do wear glasses. Wouldn't be a very efficient way of answering the question, but it would be true. So, put it this way, let's just go through all 3. If I said, how many arrangements are there? Would you agree this is the total number of ways to arrange those blocks? This is a total. We can calculate it in a minute. I'm not interested in the number right now. What about yellow together? Well, then what we do is we treat these as one item. So we are no longer arranging 9 items, we're arranging 5. We're arranging the yellow group and the 4 blue blocks. So that would be 5 factorial, except that you have to divide by 4 factorial, and that's going to be 5, right? Doesn't it make sense that it's 5, that if you have 4 blue and you have 1 group of yellow, you can put the group of yellow here, 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 or here? I mean, you didn't need advanced math to find out that that's 5. So this is 5. What is 9 factorial over 5 factorial, 4 factorial? Have you got it already? What is it?
6.
Sorry?
126.
126. So there are 126 ways to arrange all of these blocks, and of those 126 ways, only 5 of them have the yellow blocks together. Which means, and this is the analogy I typically use, imagine that I gave you 126 index cards, and on each index card you wrote one of the 126 different arrangements. And you stood beside the garbage can, and you looked at the first one, and you said, oh, the yellow blocks are together. I don't want that. And you throw it out, because this question actually says how many were there not together. If I end up throwing out in that whole 126 only 5, whatever I'm left with are the ones where they're not together. So that's why we subtract. So this is where the yellow are not all together. I mean, let's face it, some of them are bound to be together. I think there's only going to be one arrangement where none of them are together, and that's where the blocks alternate. All right, we have one more little thing to look at here. And I always describe this kind of problem as being a problem that if I was being a pain in junior high math, because maybe I got my math done early, my teacher would give this to me and it would just shut me up and keep me busy for the next half hour, which is how many different paths are there from the home to the school. So let me draw one of the paths for you. You could do this. But there's a condition: you always have to get closer to the school. If that condition of not getting closer to the school isn't there, there's an infinite number of paths. You can just go around the block again and again and again and again, right? So that's one particular path. A second path might be the following. Right? But I want you to notice something, that in all of these cases, you have to make 4 moves up in this picture. No matter what you do, you have to walk north or up or whatever you want to call it 4 times somewhere. I mean, you're going up here, you're going up here, you're going up here, you're going up there. You have to. Up, 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 up. You have to, because the school is 4 above home. And you also are making 5 moves this way. So I'm going to get rid of these. I'll just talk about the green one because I don't want too many letters on here. You're making a move left, 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 left. You have to make 5 moves left. So this green path can be coded by saying left, up, left, left, up, left, up, up, left. Right, this is the order of the person's moves. And if I change the order of these letters, I get a different path. The question is, how many ways can I arrange those letters? That's it. Each arrangement of those 1, 2, 3, 4, 5 L's and 1, 2, 3, 4 ups, each arrangement is a unique path. So how many ways can we arrange those 9 letters? Something tells me we've done this one already. Was that the 30,240? No. What was it? Raya? 126. Oh, okay, of course. 126. Of course, he says, like it should be obvious. Don't worry about why I said that. There's another way that you can do these problems, and I recognize the number 126 as a solution. That's it. If I said to you, how many ways to go from A to B here? Well, there's 2 things you have to do. You have to go from A to C and multiplication. You have to go from C to B. So to go from A to C, you have to make 3 moves to the right and 4 moves down, which means from A to C, there will be 7 factorial over 4 factorial, 3 factorial ways to do it. And just like Bobby Bear, unless he wants to get arrested, has to wear a pair of pants and a shirt, we multiply the number of ways he can put on a pair of pants and the number of ways he can put on a shirt. So now we have to say, well, this person, I'll just use a different color, red, red, down, down. Not this person, this part of the person's trip is arranging 4 items with 2 and 2 being repeated. And you just need to work that out. And I clearly forgot my factorial on the 7. I can't do that. Is this number 420? No. No. Is this first number 35? Okay. Second number 6. There's 35 ways to go from A to that joining point. There's 6 ways to go from the joining point to B. So when we multiply those together and get what I think is 210, that's the answer. Not as much time left over as I had hoped for, but more than we're used to. You got about 12 minutes here or so to work on some of these problems and to continue to ask questions regarding any of the other assignments.